All right. Hey, everybody. So today we are doing decision trees, and decision trees are really, really powerful. So even though today we're talking about decision trees, actually the next couple of topics, or the next one topic, but the next two study groups are going to be built on top of decision trees. So decision trees are a fairly straightforward model, but you'll see it being used over and over again over the next couple study groups. So decision trees is the foundation of some other models that have proven to be um, like the best performing machine learning models. So I'm excited to share that. For today, how this is structured, I'm actually going to talk about decision trees in the context of both regression and classification. I do think at some point at some sense, the regression example is a little bit easier to grasp, which is why I do want to start with talking about the regression example. But then we'll go into classification, and as usual, I'll show you all the implementation of those models. All right, so what we're going to talk about what decision trees are first, and then we're going to talk about, I'm going to flip the order of this here, 2 and 3. We're going to start with regression trees and then talk about classification trees. And for both of them, how we grow them, implementation and pruning is actually very, very similar. And then we'll end off with some quick pros and cons. Okay, so this is a flowchart. Looks very, very familiar, hopefully, but basically it helps you decide what's the word? Helps you decide outcomes based on different conditions. This is actually exactly how a decision tree works. Now, this very simple example of whether to reply, go or don't go to a party invitation depends on a couple of factors. And in this example, they're like, all right, will there be any girls at this party? Yes or no. And then also, will Miley join the party? Yes or no as well. So these are just conditions within this tree. So for a little bit of terminology, and we'll also talk about how these conditions and how these questions are being built out. Okay, so for some terminology, every time you have a condition or a question, that's a node. And the first node is called the root node, and any subsequent nodes are called the child nodes. Now, any node that represents an outcome, that's a terminal node. In addition to that, we're going along with this tree analogy. Every time you have a new branching off, it's literally called a branch. And then actually the ends are also called leaves. So we'll see in hyperparameter tuning later, they actually do really go along with this tree metaphor. All right, so let's start with regression trees, and we're going to start with this fairly simple example. This is a 2-feature data set describing professional baseball players. So over here, we have 2 features. So both of these, hits and years, these are features as part of like the X, and the color of the dots represent the Y. So here we have the color of the dots representing salary. So we're going to go in like rainbow order. So purple's low salary, red is high salary. And what we're trying to do here we're going to try and predict salary. So very, very simply, how regression trees work, or how any tree works, the idea is to try and make partitions. And these partitions end up being the questions that your tree is going to build off of. So here, let's say we want to predict salary. So you can see here, maybe on the left side, we have people with lower salary because maybe they have fewer years of experience. You can see that years is down here, and they're sort of on the lower end of the hits as well. So fewer years, fewer hits makes sense that they're slightly lower salary. And then as you branch out either way, you end up with data points that's higher and higher salaries. So one example, maybe you can say, all right, I want to partition I want to make my first node, my first root node of my tree. And maybe I'll do something like, let me just grab the pen over here. Maybe I'll do something like, all right, a good point of separation looks like maybe around like 5 years, because at 5 years, the people on the left of this boundary look to be like the blues, purples, greens, and on the right of the boundary is still more oranges, yellows, reds. And how a tree is built is you're just looking for these partitions to keep separating the data set. And then basically every endpoint, and I don't exactly remember how this data set ends up getting partitioned. I'll talk about how they pick these lines. This is going to go through a lot of partitioning to the point where you're basically going to end up saying, okay, if a data point falls within this section of our feature space, this is the outcome. Questions about this like high level concept of how trees get built? All right. So here, let's take a look and see how the partitioning actually worked. So with regression trees, more formally speaking, we're dividing the space into distinct non-overlapping regions. So for example, it does say that the very first partition over here, you can see this is like our flow chart or mind map flow chart that we saw at the very start. The first condition was whether your experience is more than or less than 4.5 years. So less than 4.5 years, you end up in region 1. More than 4.5 years, you end up on this other combination of region 2 and 3. And then they're going to figure out, okay, the next best partition is going to be actually on the axis of hits. So if you have more or less than 117.5 hits, you'll end up in either region 2 or region 3. Now, let's say we stop our tree here. We tell our tree, okay, no more partitions. How do we make predictions out of this? So in a regression tree, the prediction is basically the average of all the data points within the region. So here we end up with 3 regions, and in parentheses at each terminal node over here is the average of the salary value. So region 1's average salary is 225,000. Average here 464,000 and 949,000. So basically, if you had a new test data point, all you have to do is like, all right, how many hits do you have on average and how many years of experience do you have? See which part of this feature space you end up in, and your prediction will be one of these 3 numbers. Questions about how we make a prediction out of a tree at this point? Okay. Awesome. So how do we figure out best splits? I know that these look quite, they look a little bit intimidating, but it's actually very similar to what we've been talking about before. The cost function in regression trees is mean squared error. So actually very, because it's all relative anyways, is pretty much this, well, not the same, but it's very similar to our cost function of our linear regression. If you remember our linear regression, right, we're trying to get the least amount of error between our points and our line. So here we're using the mean squared error slightly differently, but it's the same kind of cost function. So MSE, and what the MSE is calculating is it's actually taking a measure of each data point and the average of the region. So it's going to keep choosing boundaries to reduce or minimize the error between the average in the region and each particular data point in the region. So let me actually draw out a couple examples. So let's say, let's ignore this 117.5 split so far. So let's just say we have the split of 4.5. So at 4.5, our averages, let's say it's roughly like here and here. Let's just say that this is our average salary. What we're going to do is we're going to take the salary and compare every single salary value to this average salary value. So this is the value that this is the sum that you want to decrease as much as possible. You're taking the error between the average and, sorry, this is each data point, yi is each data point, and then this is the average of all the data points within that region. So as this boundary shifts, or as this partition shifts, the average is going to change. And so they're just kind of compute where has the best overall lowest MSE. So just to decide on this very, very first split of 4.5 years, you can imagine that some gradient descent procedure has been going on. It's a very, very gradient descent. It is actually gradient descent that's going on, where you start with some initial split. Perhaps maybe they started somewhere in the middle, and then they just move it left and right, or they're going to move it systematically, of course, based on gradient descent, to figure out where is the overall lowest MSE. And they're actually computing MSE on both sides of the partition. Only after this 4.5 partition is decided, then they move on to figuring out the next best partition. And you can only partition a already partitioned space. So this 117.5, note that this line doesn't go all the way across. Rather, it just stops within that more than 4.5 region because of how the mind map works, or how the flow chart works. You could partition this space as well. Maybe you can partition it somewhere here, or you could even go and partition it this way again, but that process just keeps going on and on and on. And you can imagine with a lot of features in a in a data set, you can come up with a lot of different splits. Questions about this like cost function gradient descent process? Okay, now, oh, yeah.
Can you specify to what gradient, I guess, like to how far is splitting up the data?
Absolutely. Yeah. So these are the things that you're actually going to tune in your hyperparameters. I'm going to talk about a couple of them in a little bit as well. But yeah, you can imagine that you can pretty much infinitely keep splitting your feature set until like each data point has its own section of the feature space. That is definitely a possibility. But of course, I mean, we'll get to that later as well. That leads to overfitting, basically. But yeah, we'll talk about like tree depth is basically what you mean by like you can keep splitting over and over again until you can't split anymore. Cool. Any other questions? All right. So this approach is top down and greedy. These are two characteristics that are kind of like pros slash cons of decision trees. So a top down approach means that it's literally looking at the whole data set first, making partitions one at a time, right? Like we started without any partitions. We started by making this one over here. And the fact that it is greedy means that it has decided to make this partition first, then this partition, because at that point of time, those are the best places to split your data. However, a decision tree doesn't know that maybe in the long run, or maybe like 5 iterations through, there's a different combination or different order of making best splits. Your decision tree will not know that. So that's what we describe as greedy, because it's just deciding on what's best at that particular point of time. And we'll get more into that, I think, in the next slide. Oh, in one of the future slides, we'll talk more about that. Okay, so let's do some quick implementation of this. So in trees, and here we're doing both regression and classification trees. I'm going to go through the implementation of regression tree first, and then we'll go back to the slides, talk about classification, and then come back to here again. But we're going to talk about the same data set that we had in the slideshow. So here we have the hits, years, and salary data set. And this is, I believe, yeah, it's baseball. So we're going to use this data set first, and we're going to pretty much do the same thing that we've been doing for all of our classification models so far. We split up our X and Y, do our train test split, and here we're going to just instantiate a decision tree regressor. Over here, you'll see that we have max depth of 5, and we'll actually take a look to see what that means. So I'm going to just quickly fit this tree. And what's really cool about any sort of decision tree, whether it's regression or classification, is it's actually highly, highly interpretable. If you imagine, like if you saw that that flow chart from earlier, it's really, okay, is your value of this feature more than or less than this value? So because of that, we can actually visualize these things. So there are some libraries that allow you to visualize trees, which is really neat. So from here, you can see that, and it does take a little while. Cool. So you can see that this diagram basically shows us how our tree is being built. I did a max depth of 5, and that just means that, you know, the tree's depth will be 5. So you can see that there are 5 layers over here. And I think the number of terminal nodes will be basically up to, what is it, 5, so 2 to the power of 5? Yeah, that's the maximum number. But you'll see that some of them don't split anymore, and I'll go into this in a little bit. So from here, if like, let me zoom in, you can see that our first, oh, I know it's a little bit small, so hopefully y'all can see, but this first split is at X greater than or less than 4.5, which is the same number that we saw in the slide earlier. So from there, we just traverse down the tree. Okay, so the next one, and this is actually the one that was also on the slide, the next one we'll see, all right, well, is the number of hits, is it more than or less than 117.5? And you can keep traversing down as well. Because I set a max depth equal to 5, I can continue this on either side as well. So they're just going to keep finding best splits over and over again. Also, from this diagram, you can sort of see on each side of every split how many data points are left. So this entire data set started with only 210 data points. After the first split, on this side of fewer than 3.5 years of experience, we have 70. The other side, we have 140, and they're all going to add up to 210 at the very bottom. So we're going to keep traversing down. Oh, also one more thing is you can see the average salary value at that moment of each partition. So it starts with an average value of 543. I think it's 543,000. And here it's 203, 713. Now at the very, very bottom, you can see the same information as well. Because I set a max depth of 5, I basically say, all right, after 5 splits, just stop. Don't do any more splitting. So at the end here, we have all of these terminal nodes. And I think we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 terminal nodes. And these 20 terminal nodes, that just means that there are only 20 unique values a prediction from this tree can have, which is kind of interesting. So you can see that these values are all different. You can see that this one in this leftmost terminal node has an MSE of, well, that's the error value of 224, but there are 11 data points in this terminal partition space. And the average value here is 79.136. So anything that falls under that terminal node will get a predicted value of 79.136. And likewise, any new data point you have, you just traverse down the tree based on all of those conditions, it's going to end up at one of these. Some of these nodes do not continue splitting, right? For example, one that's right over here. You can see that over here, there's only one sample left in this partition. Therefore, it doesn't make sense to split the space anymore. So the tree will automatically know that, okay, there's only one data point here, no point splitting, because you don't want to have a partition that has no data in it. And I think this also happens a couple other places, one over here, and then one over here. So these are actually also the terminal nodes. So I should have said that there are more than 20 terminal nodes. Cool. Any questions on interpreting this graph or this visualization?
Are those terminal nodes above, could those be like, I guess, hint towards outliers?
Ooh, that's a good question. I think, yes, I think that's one way to think about it. Yeah, because if you do have a very strong outlier in your data set, it's very likely that it ends up in a terminal node. Yeah.
Okay.
Cool. Yeah, that's a good observation. One other thing, and we're going to talk about this. Oops, we're going to talk about this a little bit later. Oh, what I do? Okay. But you can actually control for the minimum amount of data points you need in a node to split it. And so, of course, if you set that to be something higher than the number 1, then you will not get those outliers as clearly. But we'll see some effects of that as well. Okay, cool. I will say, though, that once your data set gets very, very large, especially if you have a lot of features, this tree becomes way less useful, because typically you don't want to build something. Let's say you have 20 features and you only have a max depth of 5. You might not end up using every feature, which I mean can also mean that features are not very important. But if you have a much larger tree, doing this visualization does not make any sense, because it's going to start to blow up at the bottom and you're not going to be able to read this graph anyways. Cool. Well, the dot predict, we actually haven't seen many regression dot predicts since we did linear regression, so we can actually do that. From there, you can see that overall our RMSE is 353. That's the mean squared error as well. I know the focus of this phase is not regression, so we won't get into the nitty-gritty of evaluating this right now. Okay, so in terms of hyperparameters, the hyperparameters for regression and classification are quite similar for decision trees. So the most common one to tune is actually max depth. So one way that we could go about figuring, all right, what is the best max depth to use? One of the best ways to do this is to just iterate and take a look and see what the values are. So this code over here just builds a bunch of decision tree regressors with max depth between 1 and 10. And let's take a look at our scores. Okay, cool. So over here, what we are seeing is that the depths, so each one of these data points is a different regression tree, and we want to see the MSE values. So as we go more in range of depth, we actually see our MSE values start confusing. I believe this is also our test MSE. Oh, it is a cross-validated MSE. Okay, so it's neither train nor test, but it's cross-validated. And you can see that after a depth of 2, the error actually starts to increase. That is a very, very clear sign of overfitting. We'll talk a little bit more about why decision trees overfit later. But based on this graph, we want to stop at a max depth of 2, because past that, apparently the error just gets a lot higher. Questions about this? Max depth is just one of the main hyperparameters that you want to tune. I'm going to show you all some others later as well, and including the one that I talked about, that minimum number of samples before you can split. All right, so let's go back into the slides and we'll talk about classification trees. Okay, so we all know now the difference between classification and regression, basically what our target variable looks like, right? For classification, it is categorical, and for regression, it is continuous. So for regression trees, where best splits were determined by the mean squared error between the average within each partition and each data point, classification does it slightly different. So we'll talk about that in a little bit. And just to remember, what is a hyperparameter that we tune for regression trees? Max depth is one. Minimum samples before you split is another one. These will carry forward into classification trees as well. Okay, so we're going to look at our iris data set again. So in this data set, we are just going to simplify it to petal length and petal width for now. And then we have our 3 species of irises. We've seen this data set a couple times already. And here we just want to predict species. So based on this, we can see that very distinctly we have our 3 groups of our species kind of distributed in a nice way. And so based on this, you can imagine, before we even get into the math of it, probably you want to split your data set something like this, maybe like this. Maybe instead of that, you could also do something like this and then splitting it like that to get your to get your classification as well. But we'll take a look at that because the cost function for classification is slightly different. But any thoughts at this point about going from regression to classification? Pretty much the concept of how a tree is built is very, very similar, just the cost function is slightly different because we cannot compute the mean squared error of a categorical outcome. All right. So for classification trees, there are 2 main cost functions that you can actually choose between. So let me actually pull up the documentation for decision trees real quick. Decision tree classifier. There we go. So you can see that there are 2 different criteria that you can choose from. And this is basically the function to measure the quality of a split. It's basically the cost function used in gradient descent. So in here, you can pick between one of 2. You can pick either Gini or entropy. And I'll show you all the functions for both of these. So instead of using MSE, we use either Gini purity or entropy. Now, both of these are just 2 different ways to measure purity within a partition. So the Gini purity index is measured between 0 to 0.5. And over here, basically, the more pure it is, the closer to 0 your value will be. Essentially, I mean, the Gini, either of these numbers won't actually matter as much when we get to, actually building the tree, but we want to get a low as possible Gini purity index. So, and I believe it's the same for entropy as well. You want to get closer to 0 as possible, but I always forget. But anyways, this is basically a measure of how pure each partition is. So with this as an example, let's just zoom into this spot over here. And let's just say the lighter purple is iPhones, the darker purple is Androids. So how you compute the Gini purity index here is by taking 1 minus the proportion of iPhones squared minus the proportion of Androids squared. So as you can see here, let's just say we have 10 iPhones and 15 Androids. If we just work out this math, we get a purity index of 0.48. Now, if you imagine that we had 24 out of 25 Androids and 1 out of 25 iPhones, the number is just going to be closer to 0 because that partition will be more pure. And the idea of building these trees is to end up with pure leaves or pure terminal nodes. Any questions about that concept of leaf purity? Cool. I believe Gini is the default. Hold on, like the Zoom thing is always in my way. All right. Oh yeah, the default is Gini. But entropy is kind of similar. It just uses a slightly more complicated formula to calculate the purity of the leaf as well, but it works exactly the same way. If you have a mixture of different classes within one partition, you'll just get a higher value. Cool. So let's just take a look at this tree and how it was actually built. So the way that this tree was built, and this is actually using the scikit-learn output that I just copied over here. This is using Genie, and this is how they decided to split it, which for some people was kind of surprising. I think I personally also would have thought that maybe you have a vertical split over here, but based on the Genie impurity and the Genie cost function, this is what they actually decided. So they said that the first at the root node, we have 40, 41, and 39. This is basically how many of each class we start with. So we start with 40 from class 0, 41 for class 1, 39 from class 2. And the Genie starts at 0.667. The first split that they decided to make was whether x2, and x2 I believe is petal length. So whether petal length is greater than or less than 2.45. So this was actually the very first split that they made. And if it's true, you can see that the split actually made this perfectly pure. So you can see that the Genie of this section over here is 0 because we have all data points from one single class. If it's false, we end up above this partition line, and you can see that we have 41 data points from class 1, 39 from class 2, and no more data points from class 1 because they all went to the other onto the other side of the flow chart. And then the second split that they made was if petal length was greater than or lesser than 4.75, and same thing. The Genie gets better, but doesn't get to 0 because as you can see here, it's still not perfect purity. So here we still have one data point that is misclassified, and here we actually have 5. And then basically how you would classify is what the majority is. So in this case, anything that ends up here will be class 1. Anything that ends up here will end up as class 2, the middle class. And this one will be the third class. Questions about this tree?
Yeah, so is the goal to try to basically get with Genie or entropy to get like a closest to 0 if it's possible? If not, try to have like the cleanest tree, even if it's split. Like if there's 0.3 is the lowest we can get. We're trying to get terminal nodes at the end of the day. It's kind of the goal with each split.
That's a good question. So let's think about what happens if we have that. So let's just create let's just imagine that we managed to clean up those misclassified values and we get like very, very specific about where we're splitting over here. And so we end up with these tiny little partitions that can correctly classify those few data points. So if you think about decision boundary that will end up forming as a result of this, by decision boundary meaning like just abstractly in space, let me use a different color. Abstractly in space, if we want to classify these two, we're going to end up with a line that kind of looks like this, right? Anything above this orange line will be that dark purple. Anything below that orange line will be the lighter purple. We can get to this. And if you don't specify to stop at a certain level, your tree will actually automatically do this. However, it does show signs of overfitting. Whenever you have, you're considering data points that don't look like they belong in their own little cluster, that is a sign of overfitting. And whether you want to overfit or whether you want to fit to those points or not is up to you. But the tree automatically, if you don't tell it to stop, will keep building such that you end up with pure leaves. And we'll try to get to every terminal node's Genie being 0. But the reason you want to stop it is to prevent overfitting.
Got it. Thank you.
You're welcome. Anything else? All right. So let's just talk about some pros and cons of trees before we get back into our notebook. So advantages can be used for both classification and regression. We also saw that they can be displayed very visually, right? In that mind mapping, you can literally see what the conditions are for something to be classified one way or the other. Can't really say the same for some other models. For example, I guess logistic regression, you have your coefficient analysis. For naive Bayes, you would have to go back into the probabilities to figure out exactly why things were classified a certain way. And yeah, is one of the more interpretable models, basically. Also, we talked about parametric versus non-parametric when we talked about k-nearest neighbors last week. Was that last week? I don't remember. But basically, it doesn't make any assumptions of the underlying distribution of data, unlike linear regression. So you actually don't have to worry about things being distributed a certain way. You don't need any sort of like linearity assumptions, multicollinearity, doesn't matter. Also, you don't need to scale your features, which is really neat. For any tree model, it looks at each feature relative to itself. So it actually, you don't have to scale your features because it's not doing any sort of distance metric. Also, it automatically accounts for interaction, not directly, but you can sort of see that the end result of any of your terminal nodes is a result of the interaction of a couple features. So let's say back here, well, I guess this is not a good example, but if we go back to this one, this is essentially an interaction between years and hits, because these terminal nodes do have to do with a combination of the values of years and hits. So it does automatically account for interaction. Cool. So some disadvantages, a decision tree by itself doesn't really perform very well compared to state-of-the-art machine learning models. Not next week, but the week after, we're going to talk about how decision trees are used on a larger scale to actually perform very, very well. But a tree by itself doesn't actually perform very well. Couple of reasons for that. One is very it overfits very easily. The fact that, if we don't tell it to stop at a certain depth, it's going to make every leaf pure, such that, you're really starting to account for outliers that you might not want to account for. Also, this idea of recursive binary splitting, which is basically the idea of how we keep taking partitions of partitions, they make locally optimal decisions that may not result in a globally optimal tree. Because of the top-down and greedy nature of how a decision tree is built, they're basically not globally optimal. And again, not next week, but the following week, we'll talk about ways that you can actually help that. Cool. Any questions before we go back into some implementation? All right. So let's talk about our classification problem. Let me zoom back in. Here we have our iris data set again, and I'm just loading it the same way that we did before. This is the same graph as what we had in the slides. We're doing our chain test split, and we're going to fit it. And here we're going to fit it with a max depth of 2 just for now. And because I actually tested it, and the best max depth is actually 2. Here you can see this is the same diagram that came out of the slides before. If I switch this to like a max depth of 4, you can see that it does stop here, but over here it'll keep on going until, see, everything ends up being pure. But the fact that you have some partitions that only have like a single sample in them, that's a sign that you could potentially overfit. If you just so happen to have something that traverses down to one of these terminal nodes that only have like a single sample representing its partition, very, very prone to overfitting. So let's just take a look at our metrics as usual. You can see our classification reports. Because we fit it all the way such that they're pure on our train set, we do have perfect classification metrics on our train set, a little bit less of that in our test set, likely because of the overfitting. If we look at our confusion matrix, perfect on the train. On the test, we have some misclassification over here. Cool. All right, and we already talked about this. The value row in each node tells us how many observations that were sorted into that node fall into each of our 3 categories. So over here, we talked about what this value means. And then we can see that our feature X2, which was the petal length, was completely able to distinguish one species of flower from the rest. So the fact that it was able to stop, oh, sorry, it's so hard to scroll up and down. But the fact that this side was able to stop here means that that one feature was able to perfectly separate one class from the other 2. All right, and again, we can look at our max depth feature. And over here, you can see that after a depth of 2, it basically doesn't make much sense to keep on training your model. And I believe this is cross-validated as well. But you can sort of imagine that overfitting starts to become a problem. I should have done one with like train and test metrics so you can see that. You'll actually see a divergence of your metrics after the optimal max depth. Any questions about what we've seen so far? Awesome. There's one more thing I want to show you all that isn't over here. I keep forgetting to put it in here, but our model here is called C-tree. Wait, let me just make sure that is this one that I want to use. Okay. So I fit my C-tree, and within our classifier, you actually have some really, really helpful attributes. And this is one of the main reasons why I really like to use tree models. If you take a look at the documentation, they have an attribute called feature importances. And feature importances is so, so useful, especially when you want to make conclusions about your data. So let's just take a look at what feature importances does. C-tree.feature importances. Okay, so at this point, we have an array of 4 numbers, and this actually does correspond to our X train. So if we take a look at our X, oops, different X. I think it's X train iris. Oops, X train iris, there we go. So this actually corresponds to our columns. So usually what I like to do is I like to zip these two together. I'm gonna do this, zip these two, and I'm also gonna put it into a list, and we have that there. So based on this, you can see our feature importances. If you remember the notebook that I showed you all on Thursday, I actually put this into a graph as well. I don't want to get into figuring out this graph at this moment right now. But basically, what feature importance means is it's a proportion of how much each feature contributed to the purity of the entire tree. So as you saw, petal width was the feature that led to a lot of good splitting, right? Oh, I guess petal width or petal length. I might be wrong in the data. I might have matched the column names wrong, but basically they're saying that 92% of all of the splitting in our tree was based on petal width, and 5% on petal length, and about 1.25% on sepal width, and then sepal length wasn't even used at all. So based on this, you can do a little bit of feature analysis. And if you are building a model that uses a tree in any way, you can get this information out. So this is super helpful if you're making some sort of conclusions on your business case. So if you're using a tree model, feature importance analysis is something that I do want to see, or not analysis, but literally feature importance interpretation. Cool. Any questions? Let me see if I can pull up that one that we had from before. I think, have I run this yet? All right, let me just run all so you all can see what that looks like. But any questions at this point? Okay, yeah, this is an example of what feature importances can look like. Oh, Mo, are you asking a question?
Yeah, I had a question. When you said globally optimal,
Mm-hmm.
what do you mean like in terms of large data sets, data samples, small? What do you mean?
Yeah, so globally optimal is sort of a result of the top-down greedy nature. So globally optimal just means that, let's just say I built this tree. Let me use this example over here. So let's say I built this tree. Each of these splits were the best splits given the prior partition. This might not be a globally optimal tree, meaning that maybe this tree would have performed better if I first maybe split like x2 greater than or equal to 4.95 and then split x1 greater than or equal to 3.1. That's what it means by globally optimal. So this tree that was built was locally optimal because these splits were best at each point of time. But overall, they're saying that there could have possibly been a better tree, but we just don't have that as an algorithm yet.
Thank you.
You're welcome. Anything else? All right, cool. So that is decision trees. You'll see that decision trees are going to be the basis of the next few algorithms we're going to talk about, because people like the idea and interpretability of trees, but by itself doesn't usually perform very well. Before I end off, I do want to talk about some of the hyperparameters, like I said before. So these are very, very similar across both regression and classification. So first we have our max depth, which is basically how deep you allow your tree to train. Again, usually you end up with overfitting, and the default is no max depth. So that means if none, the nodes are going to be expanded until all leaves are pure or until all leaves contain less than min sample split samples. So basically, it's going to automatically, by default, just train until everything is pure. The next one was actually the one that I was talking about or alluding to before, min sample split, the minimum number of samples that is required to split an internal node. So by default, it's 2, but let's just say I set it to be something like 5. If I set that to be 5, that means that this over here that has 4 samples will stop splitting. And this one will not split anymore as well. So that's min sample sleeve. Min sample split. Min sample sleeve is kind of similar. It's basically the minimum number of samples required to be a leaf node. And so these two hyperparameters are kind of inherently related. Cool. I think that is those are the main ones. A couple of these others we'll actually talk about more the next model that we hit. Cool. Well, at this point, any questions? Neat. Well, don't forget, I think it's going to be, again, super beneficial for your project. I gave you all this assignment, and I feel like I gave a pretty good walkthrough, but if anyone has any questions or if anything is unclear, please feel free to Slack me and let me know. Cool. But yeah, that's all I had to share today. Any thoughts, comments before we close out for the week? Going once, going twice. All right, so on Tuesday, what I'm going to do is I'm going to go over the project, and you'll see that for the project, I'm also going to talk a little bit about topic 32. Topic 32 is the last topic of the phase, but it's very, very short, and I do think it is worthwhile knowing about topic 32 before getting into more modeling. It's basically pipelines and how you can automate a lot of your pre-processing steps all in a single step. So very excited to talk about that. And also, I'm also going to talk about some parameter tuning. If anyone has seen the word grid search around, that's what we're going to talk about on Tuesday as well. Cool. All right. Well, there are no further questions. Thanks for coming on a Saturday. I will see you all on Tuesday, and I hope you all have a good rest of your weekend. All right.
Thank you.
Bye, everybody.
Thank you.
Have a good weekend.
Have a great day.